Okay, so today I will be discussing about this density matrix and or say density operator. And today's lecture will be a fairly basic, and then in the next lecture I'll discuss about some of these applications of this density matrix in spectroscopy or transport theory, or say non-equilibrium thermodynamics. So before starting this density matrix, we must know two things, and that is what is a pure state and so what is a pure state? So a pure state can be represented by single ket vector, and another one is the mixed state. Mixed state, and a mixed state cannot be represented by a single ket vector, but it can be represented by ensemble of multiple pure quantum states, say psi1 or psi2, psi3, and so on. Then how do we write this mixed state? Here comes this density matrix. Sorry. And density matrix, before starting this density matrix, then how this mixed state arise? So there are two ways actually by which this mixed state arise. One is that when the preparation of the system is not known fully, then this mixed state arise. And the another one is when two systems are entangled. Entanglements correlated with each other, and we cannot describe the system as a whole. So in that case also this mixed state arise. So let's start with this pure state. Then how do we write the density matrix for a pure state? So density matrix is represented by rho, and for pure state it can simply be written as the product of wave function and its conjugate, this one. And if we this psi or the wave function can be written as a linear combination of superposition of different states. So then it can be, so suppose psi can be written as linear combination of or superposition of different states, alpha times 0 state and beta times 1 state. Then the density matrix rho will simply become product of this column vector with its conjugate row matrix, row vector. So it will be simply, if you multiply, and it will become alpha square alpha beta star beta alpha star and beta square. So this is the density matrix for a pure state, and this sum of diagonal elements is the trace of the density matrix. And it should be noted here that for a valid quantum state, the trace should always be equal to 1. For a valid quantum state, trace should always be equal to 1. Now, how do we write the density matrix? Because for pure state, we don't need any density matrix to write a pure state, because for pure state, we have information, all the information necessary to describe any system that is in its pure state. Pure state means it can be written with a single, ket vector. The need of density arose because we cannot write or we cannot describe these mixed quantum states or mixed states basically. So then suppose we toss a coin, and then suppose we toss a coin, and then we have two outcomes, either head or tail. Then there is 50% of possibility that head arrives and 50% possibility that tail arrives. Then how do we write? And suppose if head arrives, then it goes into a one state, and if tail arrives, then it goes into another state. So there is nothing quantum about tossing a coin. So in that case, how do we write this state, which is a ensemble average of these two states? That we simply write as summation over k pk, and the general expression I'm writing here, which I'll turn to this tossing a coin case, k, and where psi k is the wave function in case state, and pk is the probability of finding the particle in that particular state. So for this case, tossing a coin, we can write that this is 50% into zero state and 50% into first one state. And if we add them up, then we get 0.5 or 50%, just or we can write just instead of 50%, let me write 0.5 of zero state and 0.5 of basically in one state. And if we add them up, then it will become 0.5, 0, 0, and 0.5. So now if we note, then this matrix is basically half of the identity matrix. In identity matrix, we have this diagonal matrix elements are unity and off diagonal elements are 0. So this state is called maximally mixed state. Maximally mixed state. From now we have seen density matrix for a pure state and for a mixed state. Then next, what's the difference between this pure state and mixed state? So what's the difference between pure and mixed state? So for pure state, we have seen the density matrix as this, and for mixed state, it's 0.5, 0, and 0.5. So a thumb rule to differentiate between a pure and mixed state is that this off diagonal elements. In case of pure state, we see that off diagonal elements are not 0, but in case of mixed state, off diagonal elements are 0. So bigger the off diagonal elements, purer is the state is. So this is the thumb rule, but mathematically this purity can be
Ravi,
yeah.
just for clarification, so for mixed state, you are saying that off diagonal element is 0.
Yeah, off diagonal element is 0.
But for off diagonal element of density matrix actually represents the correlation or entanglement between the two states, right?
Yeah, that we will actually discuss later, that how
So,
this correlation comes.
so off diagonal element 0 means there is no correlation between two state, right?
Yeah,
So how,
here there is
so
no.
how
So when two states are not correlated, suppose tossing a coin, in this case tossing a coin, head and tail has no correlation. Basically, that's why these matrix elements are 0 in this particular case. But thumb of rule is more the bigger the this off diagonal elements are, purer is the state, purer is the state, and lesser is this off diagonal elements are, mixed, more mixed state is it is, and it can be mathematically defined through this purity. Purity.
I don't know. I think there is some confusion in my side, from my side.
No, so while describing this density matrix, I got your point, but that correlation we neglect here. That correlation, so the introduction of density matrix, we will see later that how this density matrix is introduced both from statistical point of view and quantum mechanical point of view. Then it will maybe become a bit more clearer.
Can I add a few one sentence that yours same thing means I just in different way means mixed state means there is basis of independent state, okay, and from there we create a means statistically average state.
Yes.
Okay, in that basis means if we select this basis as independent like head and tail, then then it off diagonal element is 0. But means if we do not choose this independent basis, then their off diagonal element also appears. For this, that's why for this example of head and tail, those are totally independent. So off diagonal element is 0. And in another example, if we take these ground and excited states, let's say, and we ground and excited state are independent. Okay, before we put any electric field or means they initially they are independent. So and finally when we means initially there is pure and mixed state are we can think same way, but when we apply the electric field, then there is a mix of these two state. Okay, that mixing is not, we cannot call it the mixed state. Okay, that mixing means there is a correlation developed due to the external electric field between ground and excited state. That's why this off diagonal term appears. So due to this means due to this external electric field, we can accurately say that this is another pure state in presence of external electric field. This is not the mixed state of 0 and 1. So mixed state depends on this. Mixed state is like statistical thing, means there is some basis, and in terms of that basis, independent basis, we can define a point, okay, where each basis contribute independently. But pure state means they are correlated, means just like ground and excited state is coupled by the electric field. Okay, so there is no basis like thing, that kind of independent basis like thing, means they are single state, means there is still one axis. Okay, means one basis is ground state we can call, and another basis is excited state. But in the pure state, if we apply electric field, this point actually change, means rotate, means this is single state, means single pure state even after applying the electric field.
Yeah, so that basically one should not confuse
Sorry?
with the superposition of state or mixed state. So that is superposition of a state, which is superposition of ground and first excited state, but not a mixed state.
Yes, yes.
Yeah, Subodip.
Subhadeep,
Yeah, it's fine.
means this is independent. Mixed
Yeah.
state means there is independent, just like StatMac. This is due to the mixed state is defined due to the connection with the StatMac. Means this in the StatMac we have independent basis. Okay. And in that independent basis we define some point from the contribution of different basis, and sampling means in that space different points means different samples. Similarly here also mixed state means, but pure state means we cannot think in terms of there is only single state which vary with due to some external field or external things, but it contains these two things just such as alpha and beta in a combined way.
Yeah.
Okay.
Okay, thanks. Go ahead.
Go ahead.
Yeah, so just to restate again. So,
in pure state, how the off diagonal elements are non-zero, because we can think that in pure state there is only one state. If there is just 0, 0, just one state, then how the off diagonal elements are non-zero?
now this pure state can be, as in the previous slide I have written here. So it can be written as a superposition of two states in different basis sets. So here alpha is the probability of finding it in 0 state basis set, and beta times in first state. So that is the psi. So now psi can be here. So psi can be represented by this density matrix, where alpha and square and beta square are the probabilities in that particular 0 and 1 state, and alpha beta is their correlation. That's what Bansi was talking. So that correlation actually comes in pure state only.
Ravi, that's fine, because a pure state can be a superposition of different states. That is fine. But in terms of density matrix, the trace of the density matrix must be equal to 1 for pure state. Okay.
Yeah, it should be actually equal to 1 for any state, not just pure state. Even for mixed state, trace should always be equal to 1.
In pure state,
no,
in pure state there is only one wave function psi. That may be superposition of 0, 1, anything. But in state of psi there is only one state, no? But if in mixed state there is summation of our psi.
Yeah, so
that's why the probability of psi appears.
If psi is only in 0 state, then off diagonal elements will not appear. Then it will be 0. But here I have said suppose psi is a superposition of two states. But to answer your question, if psi is just in 0 state, then these off diagonal elements will disappear. It will become 0. So then it will only become 1, 0, 0, 0, like this. Did you get?
Again, yes. Now, if psi is superposition of 0 and 1, then in mixed state also there will be off diagonal term will be there.
Sorry, if suppose psi is a superposition of 0 and 1 state, then
yes. Then if we let's say summation over psi again in mixed state, there is summation over psi p psi. Then also that off diagonal term will appear, no?
For mixed state, the trace of rho should be less than equal to 0, right?
Yes.
For mixed state, yes.
Less than equal to 1, right? For mixed state, rho should
no,
be
so that's what. So the trace is always equal to 1, but that's what I was now going to describe. That for purity, actually the trace of rho square
is trace of rho square.
If it's equal to 1, then it's a pure state. And if
Yeah.
it's less than 1,
Less than 1.
then it's a mixed state.
Yeah.
So,
Rose
I want to add one sentence in that discussion, that I always think that means this will not be confusing. Mixed state means just like statistical basis. Okay. In case of statistical mechanics, there is independent basis and we define a point in that space. But pure state means that is Hilbert basis. Okay, that alpha beta, then those are like follow the same rule like Hilbert space. There should be a correlation, means alpha beta star or beta alpha star. But in the statistical mechanics, the fundamental a priori thing is that we have to select the means independent basis. So then it will be not confusing if we keep in mind that difference. Means mixed state means we need those bases because some observable depends on varieties of independent other things. Okay, just like statistical thing, mixed state means statistical and pure state means totally Hilbert, means there is no other independent processes there. So Hilbert and statistical, this way we can, means this is a quick way we can just keep in mind whenever we read or see this kind of thing, different thing. So is it?
Yeah, it's fine, but I think there is still some confusion.
Yeah.
Okay.
So what's the confusion, Subhadeep?
No, it's fine from my side because I can understand the pure and mixed state, because for the pure state, let's say rho equal to just k top psi times bra of psi.
Yes.
The mixed state it is in the statistical sense, that is summation of, let's say, p psi, then k top psi, then bra of psi, right? So p psi can vary from 0 to 1. So it is in the statistical sense. So that's the difference between pure and the mixed state. Because the other Subhadeep was talking about the correlation between the off-diagonal elements, relationship between the off-diagonal elements and the correlation. So I think that's the confusion. So you can just clear that.
Yeah. So Subhadeep, means the other Subhadeep. So can you just restate so that we can?
No, my question was that in pure state, let's say there is no superposition of 0 and 1 state, only psi is there.
Okay.
So then the off-diagonal term will be 0.
0, right.
Now in case of mixed state, then we have to take the superposition of state and then maybe coherence also. So if there is coherence, then there will be off-diagonal term will be non-zero. And if there is not any coherence, then that will be 0. As you written here, 0, 0. The superposition of state. Now
Okay, so
if we
yeah,
that's up to that is clear. Yes. Now now if we consider that if psi is superposition of 0 and 1, then it appears that in pure state the off-diagonal term will be alpha beta star beta alpha star.
right.
In that case also, now if again in case of mixed state, now we have to consider the sum over t psi. So then again, and then also I think then also we have to put that psi in terms of 0 and 1 basis. Again, then there will be summation over t psi. So I think there will be again octagonal term appears.
Yeah, then off-diagonal terms will appear, but in that case, the density matrix will not be 2 by 2 matrix, because now for a single state, suppose the mixed state is ensemble average of 2 states, and single state itself is superposition of 2 states. So in that case, the density matrix representation will be different. So diagonal matrix, diagonal elements will appear in that case, but suppose it is a 4 by 4 matrix, then only one two element will appear. Get to my point?
Okay, that means here you have written that the pure state, the density matrix for pure state, that operates on the basis of 0 and 1, but the density matrix written for mixed state, that operates on psi.
Both are actually occurring on psi, but in the case of mixed state, the psi is not superposition of any state, because I have
Okay.
taken example of tossing a coin. So tossing a coin, there is nothing quantum about it. You cannot express it as a superposition of any states. It's just either head or tail.
Okay, I understand.
Yes,
Okay.
yes. Means, another quick point of view that just like statistical, if you correlate with the statistical thing, the different ensemble creates a average experimental thing. Okay, this is the mixed state. So in each ensemble, we can think each ensemble is consist of pure state, and what we measure with in terms of sum of the all ensemble, this is the mixed state. So this is the direct connection between mixed and pure and mixed state. Means in ensemble, each ensemble point is the pure state, and those different ensemble create a mixed state. Okay, Ravi.
Yeah, okay. So so this purity can be defined by the trace of the rho square, and if it is equal to 1, then it's a pure state, and if it's less than 1, then it's a mixed state. Now, how do we represent this pure and mixed state? Representation of this pure and mixed state on this Blount sphere. So for a pure state, the vectors are of unit length in Blount sphere. So we can represent any pure state. Suppose this is 0 state, this is one state. So these are of unit length for pure state. So this length of vectors is equal to 1 unit. But in case of mixed state, so these vectors are of not unit length, so they are reduced. So take the example of our tossing a coin, which was like getting ahead is 0.5 or say 50% in of 0 or 0.5 of say 1. Then it will simply be the product of the probability of finding it in 0 state. So 0 state means head, and probability of finding it in say 1 state. So just multiply the probability of that particular state with its vector. So in that case, so suppose it is 0.5 here, in multiply by 0 state, and 0.5 multiply by the first state, and if we add them up, we get a dot in Blount sphere. So this maximally mixed state, can be represented by a single point in the Blount sphere. But if it's not maximally mixed state, then it is just multiplication of the probability of that particular state into its vector. So it can be like suppose here it is, suppose X state, and if it is mixed or it's the ensemble average of 0 and X state, then the resultant vector can be 0.5 times into 0 state, 0.5 times 0 state, and say here probability of finding it in X state is suppose something point X, suppose 0.5, same, then it will be 0.5 into 0 state plus 0.5 into X state, and the resultant vector can be like this. Okay, so with this, now let's define this density matrix. So what is density matrix? and it literally depends on how we see it. So mostly we are aware of this statistical view of density matrix, so which defines statistical view, which defines that it is the quantum mechanical counterpart of this classical distribution functions. So it is the quantum mechanical counterpart of this classical distribution function. But this is the statistical view only. There is another view, that is quantum mechanical view. And which says that it is the most general description of an open quantum mechanical system, so which cannot be described by a wave function, single wave function. So this quantum mechanical view is the most general description of a quantum mechanical system, most general description of quantum mechanical system, which cannot be defined by a single wave function of an open quantum mechanical system. What do you mean by open here? So open means it is connected with bath. Not closed means is we are only just system. We have only system and there is no surroundings. But an open quantum mechanical system means it is connected with bath also. So it is the most general description of an open quantum mechanical system which cannot be described by wave function.
Ravi,
Yeah.
I could not understand that what the meaning of the statistical view, like the quantum mechanical counterpart of classical distribution function.
Yeah, so when in statistics we have this, suppose there is a particle and just a moment. Yeah, so classical distribution functions means suppose any distribution function, say p, so it depends upon this position of particle and momentum of this particle. So if we know the position and momentum of any particular particle, then we can define that its probability of finding that particular particle in that particular space. So that is defined by this classical distribution functions. So this is for just one particle, and depending upon different positions and momenta, we can distribute our particles in whole space.
Okay.
So that distribution function defines that which particle is located at which position and which momentum.
Okay.
So
what?
So in quantum mechanics, so this is like counterpart of that classical distribution function. So this the density matrix, it actually defines that how do we find that particular quantum mechanical particle in particular state given by this its specific probability.
Okay.
And that yeah go on.
No, you go ahead.
Yeah, so that we'll also see in detail. So these are the two views of defining a density matrix. There is another view which is an operational view. So it is more of a combination of both this quantum mechanical and statistical view, and it says that it's the most convenient way to collect all these parameters. So it's basically from like combination of both statistical and quantum mechanical view, and it was introduced by Fano in 1959. So it is the most convenient way to collect all these parameters that are of our interest. Suppose we want to measure any system, so there are certain parameters that we can measure. So to set up an experimental, suppose to set and or to develop an experimental setup, we need certain parameters. So all those parameters of our interest for a given experimental setup. And describe their behavior. So this is more of an operational point of view. And so this density matrix was introduced by von Neumann in 1927 to introduce those statistical concepts in quantum mechanics. And what motivated, but so before starting that, so some sources also say that other people like the this Landau and also Bloch, they also used the density matrix formalism in the same year 1927 independently. And also Dirac used this same idea of density matrix in 1929 without naming it as a density matrix. So just did not name it as a density matrix, but he has also used the same idea. But how do this idea developed? So first is why it is needed. So as I mentioned, we cannot describe a mixed state with the single wave function. So in that case, we need this density matrix. So to introduce this statistical concepts in quantum mechanics, so basically von Neumann formally introduced this density matrix approach. And as we know, so why most of our these physical systems, it consists of many particles or many degrees of freedom in real systems. So real systems contains many degrees of freedoms or many particles. Or many degrees of freedoms. So it is impossible to specify completely state of such systems. Then, or if we say it in another words, so it is not possible to describe the quantum state or quantum mechanical system, that undergo general quantum operations, such as these measurements using this exclusively states that are represented by ket vectors. So to overcome these problems, this density matrix was introduced, and the idea came. So the motivation came from this statistical only. So physicists, always used this representative ensemble thing. Representative ensemble. So this representative ensemble is basically collection of identical systems, and it's not the whole physical thing. but it's the collection of identical systems. And it turns out that if we choose this representative ensemble wisely, then, and if we measure any physical quantity, if you want to measure, suppose, any physical quantity, say momentum or anything, then this representative ensemble, and if we choose it wisely, then the average, average calculated or computed over this representative ensemble is turned out to be equal, or if we ignore, suppose, fluctuations, then it turns out to be equal to the actual physical quantity of the system, the whole system. So it motivated scientists to use the same idea in the quantum mechanics. So they thought that it can be a similar concept, or the similar idea can be used to describe the quantum mechanical systems by these representative ensembles. And some example of these are the quantum systems in thermal equilibrium, non-equilibrium, those time evolution, transport theory, and entanglements. So that we will see in the application part. And before introducing density matrix formally from the statistical and quantum point of view, another aspect of this statistical mechanics is the use of the wave function itself. This psi in quantum mechanics, you know that psi square tells us the probability of finding any particle in any state, psi. So the probability of finding particle in any state, psi. So this probability is already there in quantum mechanics naturally. So because even if we know, so say for pure state and single pure state, we know all the information about the system. Still there is this probability sitting there. But if we see the classical mechanics, and to describe any classical system, if we know the all the parameters of a classical system, then we can completely describe the system. So probability is more naturally sitting in this quantum mechanical thing rather than classical thing. So to introduce these things, one needed this quantum mechanical analog of that ensemble density or the classical distribution functions. So to introduce in quantum mechanics, we need this ensemble density, and which is operator in quantum mechanics, and that is our density matrix or density operator. So now let us introduce density matrix from statistical point of view. So statistical point of view is that we need this ensemble density, or say the ensemble density for quantum mechanical our quantum mechanical system. And let us consider we are working in this grand ensemble. In grand ensemble, we have total number of particles are not same. N is total number of particles are not N is not conserved. grand ensemble means this grand canonical ensemble, and suppose we have n such systems where n is not constant, and we have n such systems and described by their this wave function psi k, where psi k and this k varies from 1 to 1, 3 and n. So and psi k is their wave function in any kth state where k varies from 1 to n. And if we write this psi k in terms of
Ravi, one small thing.
yeah,
Those two ends are not same, na? Means so same different notation will be helpful. In prime in one means n means number of particle which is not constant, but system means number of ensemble. So different notation would be helpful. Otherwise,
okay,
later it may confuse.
okay, sir.
In prime or in one.
Yeah, okay. Then I'll keep this as n prime. So psi k is their wave function where k varies from 1 to n, and we can write this psi k as an orthonormal set also, where it is as a combination. Cn is the coefficient and phi n is the state. And for simplicity, suppose if we, so this is orthonormal set, and suppose simplicity, we assume that this phi n or this psi are independent are not vectors, so they are spin free. And now suppose we want to measure any physical quantity a, then we know that expectation value of a can be given by this 1 by n summation k summation mn and this cm cnk and this amn, where this amn are the matrix element of this operator. These are the matrix element of operator, which are basically, we know this simple thing from our quantum mechanics knowledge, this thing, because we know that expectation value of any operator a is basically given by 1 by n, and then k varies from 1 to n. Simply this psi k star a and psi k data. So these amn are the density matrix elements of the operator a, and now define this rho mn, which is 1 by n. Now let's give this equation. This is equation first, and summation for k cnk star, and then simply cmk. So these k are all same. Actually, sometimes I'm writing this otherwise. Yeah, so these k are same, and these are the matrix elements of density matrix. So these are the matrix elements of operator, and these are the matrix elements of density matrix. So then look at this equation here. Operator a, expectation value of any operator a can be given by this double summation. One summation is over this ensemble average and another one is for the operator. So this A operator can be written as the summation Mn, and now let's give this equation to Amn. Just I'm now putting the values of Amn or this thing in the previous equation, Amn and rho Nm. So this is the value of our expectation value of the operator A, and which is equal to simply trace of this rho and A. Yes, let's give it this equation 3. Now focus on this equation 3, and we can see it's not a single average. Expectation value of A is not a single average, it's a double average. Why? So one average we have seen is from equation 1. So this average is over the coming from equation first on the operator thing, and second one is the this okay, so this first thing, it will always remain there when we find the expectation value of any operator. So even if we know the our state completely, say for pure state, even though this will always remain there, this Amn, because it's a quantum coming from this quantum thing, that how do we find out the expectation value of any operator. But this rho Nm is coming because of the statistical averaging, or these, because these are the matrix element of this density matrix, and it is coming due to lack of our knowledge about the system. So there are two averages here that are sitting in expectation value of A, and from this equation to this equation we can, so this is K, from equation 2 this is CK, Cn K star and Cm K star. We know, we can say that easily, that this rho Nm is equal to rho Mn star, and this is the condition of any operator to be Hermitian. So then rho is a Hermitian, and from, if we suppose our operator here, if the operator is unitary, then suppose our operator is unitary, just one, then we can find that this density matrix is normalized. How? So this simply, just if we put 1 in place of operator, then it will become this equation here, equation 3, 3. So it will just become trace of a rho, and which is equal to 1. So this, and let's give this equation as 4th and this as 5th. So our density matrix is Hermitian and it's normalized. Now if we combine equation 4 and 5, then we can see that these diagonal elements are always real, because this, it's only possible when the elements Pn m is equal to P, rho Nm is equal to rho star Mn, if the elements are real only. Real, this thing, meaning if we change here, what I am saying is, if Pnn is equal to rho nn is equal to rho nn star, then it's only possible if the elements rho nn are real. And from equation fifth, we say that trace is equal to 1, or this density matrix is normalized. So it means the diagonal elements are always equal to 1. Diagonal elements means, sorry, the sum of the diagonal elements is always equal to 1, which means these diagonal elements of density matrix will always be in between 0 and 1. And this rho nn, or these diagonal elements, this tells about the probability of any particle in state phi n, or it tells the probability basically. So the rho nn basically is telling about the probability of finding any particle in state phi n. Yeah. And if you remember our 2DIR lecture, so there I have also mentioned that how these diagonal elements are telling about the probability, while off diagonal elements are tells about this coupling and population decay. So well, that we will see again when we will discuss the application part. So just to restate again, we can say that this trace of rho square is equal to 1 if it's a pure state, and it's less than 1 if it's a mixed state. So for pure state, so basically this square is actually rho square is just rho. And so one thing again, just to restate here, that this operator is now averaging over two different properties, also two different observables. One is this density matrix and another one is the operator. Now let's see how this equation of motions suppose our wave function that we were now talking about follows this Schrodinger's equations. Suppose psi follows Schrodinger's equation. So in that case, we know that Schrodinger equations is just Hamiltonian and I cross. So this dot is actually this time derivative, or simply we can write this as iota cross.
Ravi,
Yeah.
can you go back to the previous slide?
Okay.
One more slide. Okay, where the density matrix was defined.
Okay. So
The density matrix you have designed here. I'm just little bit confused, like why we are calling this as a density matrix. What is the role of density here? Like from where the density is coming out?
So the density
Like
is coming through these coefficients. These are the coefficients of finding a particle in kth state.
This is the coefficient to
Coefficients, this
Mhm.
finding the particle in kth
Mm.
state. So these are the probabilities, basically probability of finding any particle in kth wave function, suppose.
Okay.
Here just see the basic definition where here. So pk is the probability of finding in kth state. So this pk is actually that ck, or sorry, cn or cm. These are the coefficients. Coefficients means probabilities.
Okay. Got it.
Ravi, just a small
Yes.
thing that go to that equation where pk is defined, where rho is defined.
Yeah, rho is defined
Here.
here.
Means if we have only one basis in one Hilbert basis, and then rho is finding the state in that statistical basis. Okay. But here means here these two density in two subdivision means density rho mn means density density in Hilbert basis. Okay. Rho density mn means mn subscript means in Hilbert basis. What is the density of particular means here means actual density, means what do you mean by density, but means what is the correlation between two Hilbert state. Okay, overall correlation. So I think it is basically same, but we have to keep in mind that here two different things. One is Hilbert thing and one is statistical thing. So overall density means if we can talk about the density in the stat basis or density in the Hilbert basis. So the density can here mn means density in the Hilbert basis. So that's why we add all the statistical combination, means summation of k.
Okay.
Just one addition to your answer. Okay.
Yeah.
More clarify. And one more thing.
Yes.
You earlier defined that grand canonical ensemble for this derivation, but this is there is no means this is applicable for any kind of ensemble, na? NVT, NVN.
Yeah, it can be.
There is
can
no
be true for
grand canonical ensemble. No.
Nothing special. Just we have taken grand canonical to show that our total number of particles are not same here.
But here in the derivation, it is exactly the same thing, because here nothing in between, nothing grand canonical thing appears. So this discussion is exactly same for all kind of ensemble. That's one.
Yes, actually here you are only talking about the ensemble of systems, so not the particles. So for canonical, grand canonical, the derivation will be the same.
Exactly same.
Yes.
Yes.
Okay. Yeah. Okay. So this is the Schrodinger's equation, which we can also write simply like this. And if we just modify a bit, then it will transform to. So this is now the here also. The dot product are this means in the red color. So these are the time derivatives. So it can be written as simply and this is the famous this Lewell won Newman equation. Which is the counterpart of the Lewell equation in classical mechanics. So up to now, so this can also simply can be derived very. So if we want to derive it, can be very simple to derive this equation simply by the psi thing. So till now we have been working in Schrodinger's representation. So it is also important to note that because sometimes it's become confusing. So in Schrodinger's representation, operators are, suppose this is the operator and this is the expectation value of operator, or just okay. So these operators are assumed to be time independent. And this wave function is basically, so the time dependence comes in the wave function. It is time dependent in Schrodinger's notation or representation. So this is important to note that in Schrodinger's representation, the operators are time independent. And the time dependence comes through the wave functions. But there is another representation that is called Heisenberg representation. Where the time dependence comes in the operator part. So this is the operator. So it is now time dependent. It's just these are the two different representations, and psi is considered as time independent. So in the same, if we write this equation, we will want Newman equation. Then in Schrodinger representation, it can be written like this. So now here this operator is time dependent. So the time derivative is taken over the operator. And simply like this. So this way we have introduced this density matrix through statistical mechanics. Now let's see quickly that how we can introduce it through quantum mechanics. So it's quantum mechanical.
Ravi?
Yeah.
So how much time do you need?
No, it will be over just in 10 minutes or maybe less than that.
Okay.
So this, now let's see the quantum mechanical approach of introducing this density matrix. Now suppose we have a system with many degrees of freedom, and there are x degrees of freedom which we are interested in, and few degrees of freedom, so that are other degrees of freedom which we are not interested. And suppose we want to measure any operator A or any physical quantity, suppose A, that we want to evaluate, and it's only the function of x only. So these are, because these degrees of freedom are of our interest, and these are other degrees of freedom. So this is, now I'm talking about the isolated system with a bath connected to it. So this x degrees of freedom that are of our interest, and the q degrees of freedom, other degrees that are other degrees of freedom, are basically bath degrees of freedom. Then in that case, expectation value of A will be given by this psi star, which is a function of q and x. Simple, just normal expectation. How do we evaluate expectation of any operator? Then psi qx dq and dx. And if we define now let's define the density matrix by the equation. So this density matrix will also be now depend only upon our x degrees of freedoms, and which is basically psi star now qx prime and psi qx dq, and taking average over other degrees of freedom. So this is our equation of our density matrix. We have just defined it, and it's only depend upon the x degrees of freedom. And then if we insert this equation in our this original equation, say this is equation number 7 or what, okay, say A, then our equation becomes double integrals x prime rho x dx, just putting now the expression for density matrix, and then x operator, because it also depends on our x degrees of freedom, x prime, and which is now equal to trace of our density matrix and trace of our operator. And this we know that trace is equal to 1 because it is normalized, density matrix is normalized, so this trace is equal to 1. And let's give it equation B. Now you can see that this equation B is similar to our equation 3. So here also expectation value of operator A is given by the trace of density matrix and this operator A, and here also we see that this expectation value of A is the trace of density matrix and this operator A. It means that the density matrix that we have defined in statistical point of view is same to the density matrix that we defined in our this quantum mechanical point of view. So the two approaches are same in the sense that now the density matrix is similar because now the expectation value turns out to be same for both the approaches. So either you define it from this quantum point of view or a statistical point of view, the end will always be the same. Then how do we correlate this classical and quantum point of view? So we have seen that in this quantum point of view, we have taken average over all the path coordinates, average over all these path coordinates, q's. See here, this thing. We have taken average over these path coordinates. So we are seeing collectively that how the ensemble average of these path coordinates are affecting our system of interest, or the system of interest. And it is same as we have taken the ensemble average in statistical point of view. So the two are similar. And if we see the equations of motion in quantum mechanical point of view, then we can write. So this is again the time derivative over x only, and where x is this thing. So this is the equation of motion in quantum mechanical point of view, where h is the Hamiltonian, and this rho is our density matrix. So finally, this density matrix in quantum mechanics is basically the coordinate representation of density matrix in statistical mechanics. Just that. So this is all, and in the next class I will be discussing its application. Applications of density matrix. So in transport theory, polarization experiments, and also in how do this equilibrium state mech can be described. And one more application that I don't remember now. Yeah, so that then we will see how this density matrix is used, and also in our in polarization experiments I'll also discuss about how we use this density matrix in our vibrational spectroscopy. Yeah, so now I'll ask if there are questions or comments or anything. So anyone? Any question, query, or any comment?
I think question were asked during your whole.
Okay, then you may stop recording.
Okay. So I am stopping the recording. If anyone have, you can. Anyone is thinking about some question, then also you can.
Yeah, or also if.
Okay, I will stop recording.